So we finished up mean value theorem last time, but there was something at the end that I didn't talk about that I really wanted to address. Let's take a look at this equation. X cubed plus e to the x equals 0. And let's show this equation has exactly one real solution. So we're stepping pretty far away from anything we've done at this point. All right, this is not tied into the mean value theorem where we were trying to find that point where the tangent line was parallel to the secant line. This is totally different. Okay, so if it looks different, it should. All right. We have an equation, and if we try and solve for x here, what we're trying to show is that there's only one x value that's a real number that would solve this equation. There's only one. So if you go through and you go through all the different techniques that you've learned in algebra of how to solve equations, this doesn't fall into any of the group categories that you've ever learned. I mean, you know how to solve exponential equations. You should know how to solve polynomial equations. But the trouble you run into if you try and get x isolated here is like, let's say you try and get clever and you're like, okay, I'm going to put e to the x. I'm going to move the x cubed to the other side, so something like that. And then I know that if I can get the x out of the e by coming in with natural log on both sides. So you come in, you bring in your natural log on the left side, and you bring in your natural log on the right side, something like that. Then you're going to get, on the left, the x will pop out, right, because natural log and e wipe each other out, and you get x. But the problem over here is that x is still trapped. So you're trying to get x by itself, but to release x from e, you have to trap it on the other side in natural log. So does that make sense? You just no way you're going to get x by itself. So there is no algebraic way to solve this equation. Right? We just don't have a way of doing it. But we're being asked to show it has an answer. It's not asking us what the answer is. Do you all see that? It's not asking us find the solution. It's saying prove to everyone that it does have an answer and that there's only one of them. All right? So here's what we're going to do, and this is kind of cool. What we're going to do is we're going to look at the left side of this equation right here, and we're going to look at that as a function. I'm going to call it f of x is x cubed plus e to the x. Now, whenever we take a function and we set it equal to 0, doesn't that correspond to the x-intercepts? Yes? So this equation now for us corresponds to the x-intercepts of the function f. So we're looking for the x-intercepts of this function. Yeah? Yes? Yes, yes? Yes. Okay. That's what we're looking for. I need to show you that there's only one of them. There's only one x-intercept. So what I'm going to do now is I'm going to plug in a number. I'm just going to take a guess at this. What would happen if I plug -1 in? Will I get lucky and this turn out to be 0? Let's see. What's -1 cubed plus e to the -1? Well, -1 cubed is -1, and then plus e to the -1 is 1 over e, isn't it? That's not 0, is it? But is it positive or negative, this number? It's negative, right? 1 over e, that's 1 divided by 2.718 about. That number right there is smaller than 1. So if I add -1 to it, this should be a negative number. Agreed? So does everyone agree that's less than 0? So if I were to graph this right now, if I were to be graphing this function, I know that at -1, it's somewhere down here. My function is somewhere down there below the x-axis. And now let me plug in, I'm going to guess again, how about 0? What do I get if I plug in 0? I get 0 cubed plus e to the 0, and that's just what? 1. And that's a positive number, isn't it? So at 0, I'm up here somewhere. Is that enough to convince you right now that I have at least one x-intercept? Yes? Because I have to connect these 2 points together, don't I? And I'm not allowed to jump or break or split my graph, like, go and then just go up and all of a sudden up here, because why? It's continuous, right? This is a continuous function. E to the x is continuous. You add 2 continuous functions, you have a continuous function. So I know right now, for sure, I have at least one, right? It could do this, though, and I could have maybe 2 or 3, right? So how do I convince myself there's only one? I could check another point, yeah? Tell me about this. If I draw this, and it comes back down and goes back up like that, if I'm going to have more than one x-intercept, my graph will have to go up, and eventually, won't it have to come back down and then go back up? So in terms of what we've learned about the derivative and how it's connected to the function, doesn't the derivative being positive mean kind of like the graph is going up? And doesn't the derivative being negative mean that the graph is going down? So again, if I'm ever going to have more than one x-intercept, my derivative will have to switch from being positive to negative and then back to positive, won't it? But if the derivative is always positive, could it ever do this? It could never do this, could it? Because if the derivative is always positive, that means it's always going up. So that's what I'm going to look at next. I'm going to look at the derivative. What is the derivative of this function? So from this right here, my conclusion here is I have at least one x-intercept, right? Which means there's at least one solution to this. It's somewhere between -1 and 0, yeah? At least one x-intercept in the interval 0, 1. Sorry, I meant to say -1, 0. Everyone agreed with that. I have at least one x-intercept in the interval -1, 0. So it's somewhere between there. To convince myself that there's only one, I look at the derivative. The derivative of f is what? 3x squared plus derivative of e to the x? What can you tell me about that function in terms of whether or not it's positive or negative, whether it ever switches? It's always positive. Agreed? Take any x value, doesn't matter what it is, plug it in here. You square a number, it's going to be what? At the least it would be 0, right? Any other number, we're going to square it, we're going to get a positive number. Times 3, the worst case scenario, we get 0, or 3 times a positive number. E to the x, always positive, isn't it? E to the x, if you graph it, is always above the x-axis. So we're looking at a number that is possibly greater than or equal to 0. Sorry. This right here is always greater than or equal to 0, plus a number that definitely is greater than 0. If you put these two together, would you agree that that has to be greater than 0? Yes? So that means that my derivative is always greater than 0 for all x. Yes? For all x, my derivative is positive, which means my graph is always going up. And if my graph must always go up, and I have to connect these 2 points together, you'll never turn back, right? So I have to go up, and I know I can't pick up my pencil, so somewhere in there I cross through. I cannot turn back. Now I've got to keep going up. So I've got to connect somehow in there. So there's only one answer. Understand? So this right here, my conclusion from this, therefore, there's only one x-intercept. Now, the actual way that a computer would solve this is using something called Newton's method, or some variation of Newton's method, which is in 4.5? No, 4.6. 4.6 is Newton's method. And we would actually figure out in that section how you actually find that number. Right now, we don't know what it is. We just know it's somewhere between -1 and 0. All right? Questions? Do y'all understand the logic behind that? What's that?
Showing us that because it's going to be on the test.
I don't like to give this as a test question only because, I mean, what's your answer? Your answer is actually just some logical steps, right?
Right.
It's just more of an interesting result that an equation that we would normally not be able to solve, we actually do know that there's only one answer to it, right? That's all. Okay. All right, now let's get on with today's stuff. So the mean value theorem, which was last class, is an important theorem in mathematics. I was looking through some of my proofs that I did when I was in school studying math, and I had to prove like the fundamental theorem of calculus and some other things, and you use the mean value theorem quite a bit. But in this class, it's pretty much what we did last time. That's it, and we move on. Okay, we're not going to really apply the mean value theorem a whole lot more. So I want you to look at that mean value theorem as almost like we took a little pit stop. We did that, and now we're back on the road of looking at graphs and like highest points and lowest points again. Okay. So what can we do? You know, as of now, up to this point, right? Here's what we got. If we're given a function f, which is continuous on a closed interval, right? If we have a continuous function on a closed interval, and the derivative exists on the inside of that interval, we can find the absolute max and min, can't we? We can find absolute max and the absolute min. And what method did I call this? Anyone remember? Closed interval method. Okay, and to do this, we used the closed interval method. Let's see if we can summarize it in just speaking it out. Well, I'm not going to write it down, but what is a closed interval method? How do you do it again? Take derivative. Check domain.
Then solve for x.
Set the derivative equal to 0. Figure out where the derivative is undefined. Get those points. We called those critical numbers. Take those and the endpoints and plug them into the original function. That's the closed interval method. Find your critical points, find your endpoints, plug those into the original function. Make sure that those points lie within your interval, right? And then you're off to the races. You can figure out which is your highest and lowest point. So today, we move away from this method, and now we stop restricting our function to a closed interval. We allow the function to just be defined, however it's defined, and we try and somehow determine not necessarily the absolute maximums and minimums, but just where these humps are occurring. Where do we have local maxes and mins? Where do those occur? So to get us going, this section 4.3 is called derivatives and the shapes of graphs. So derivatives and the shapes of graphs. What we're gonna see here is that the first derivative of a function tells us a lot about what a function looks like. But the second derivative also adds more detail to our picture. So the first thing here is the definition for increasing and decreasing. All right. So we all hopefully know geometrically what we mean by a function that's increasing versus a function that's decreasing. So I'm going to show you a function now. I'm going to draw a picture. Something like that. This function is increasing anywhere it's going up as we as we look at it like we read a book from left to right. So it looks like for us, let's see, let me call that point, call it A. And then this lowest point here, I'm going to call that B. And then in red, what I'm going to do is I'm going to label where the graph is going up. And then I hope you'll agree with me. Should be going up this way, right? We're going up, going up, going up, all the way till we get to that point, right? And I'm also increasing over here. Up, up, up. My graph is going down or decreasing here, 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 right? So what we know about this is that if I were anywhere on the curve in the red, if I were to pick a point, any point over here, right? And I were to take the derivative would represent the slope of the tangent line, right? I can be sure that my derivative would be what? Positive, right? Any point here, my derivative is positive, 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 positive. Until I get to the top, the derivative would be 0. Then when I'm in the green, the derivative would be negative, 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 negative. And then when I get to the red, positive, positive, positive. So if, all right, this is kind of the big conclusion, if f is continuous on an interval, capital I, and this time I'm not telling you that the interval is closed. That's the big change here. If I wanted it to be closed, I would put brackets and say AB or something like that. I'm just saying an interval. How many different types of intervals are there? You could have like an interval like A, B. You could have A, B. You could have bracket A, B. You could have A, B, right? You could have what we call an open interval, half open, or you could call this half closed. It's either way. This would be, oh, those are the same, sorry. This would be half open or half closed. This would be closed, right? So now any of these, okay, any of those count here. And also A and B can be infinity, except you wouldn't use brackets on infinity, right? So you could have like infinity, negative infinity to infinity. You could have negative infinity to 4. So there's a lot of different things we could have in there. So let's say that f is continuous on an interval, and f prime exists in the interval, and the derivative is positive in I. Then what can we say? Then f is increasing. So then f is increasing on I. So that's our connection between the first derivative and the function. So if your first derivative is ever positive on some interval, you know that your function is going up on that interval. Make sense? What about the decreasing? What would this change to? Everything would be exactly the same except what? If this is less than 0 in I, then the function is decreasing. So instead of writing all that, is it okay if I just put it in green, or you want me to rewrite the whole thing? It's in the notes also. Look, if this is less than 0, then this is decreasing. Then your function is decreasing. And that's a lot of information. You can tell when a graph's going up and down just by looking at its derivative. That's the whole point of it, all right? That's what we used in the previous problem where I was showing you that that thing only had one solution. We were counting on the fact that the derivative was positive, which meant it couldn't turn back. Now, that's what the first derivative tells us. The second derivative is something else, all right? So now let's talk about what's called the concavity of a function. So we have the idea of increase, decrease. Now the new idea is concavity. Now that comes from the word concave, you know. And you know, we've seen like concave before. What that, you know, like a lens is concave.
Is it,
Yes.
what is the possible? When the function is like bigger or like less or more than 0, it's going to go up or down?
Yes, there's something like that. Yes, the concavity has to do with the shape of the graph either looking like a smile or a frown. Okay? So let me get to it. Let me draw you a picture. I'm going to look at that same kind of graph that I had there a second ago. Doesn't have to be exactly the same, but something like this. But this time I'm going to highlight some regions, and I want to see if we can somehow determine what these have in common. So this is the green section, stops there. And then the red section right here goes like this. So does the green and the red on that graph represent where the graph changes from increasing to decreasing? No, because look, if it was increasing and decreasing, it would have stopped there. The green would have stopped there, and then the red would have picked up and stopped here, and then the green would have picked up. So somehow this green and red does not distinguish where the graph goes up and down. It's something else. So do y'all see what it is? How do you mean changes direction?
Well, like within the green, it goes from increasing to decreasing.
Uh-huh.
And within the red, it goes from decreasing to increasing.
It does. It goes from increasing to decreasing, and then decreasing to increasing. Hold on. Let me see if there's something I could look at. If I graph, how about if I graph this? Watch. I'll give you another one next to it, so it'll be. With that function, so what I'm trying to do is come up with an example that will kind of challenge the idea that the green and the red have anything to do with the increasing and decreasing at all. This function is always increasing, isn't it? Yeah. But I'm still drawing a green and red. It has to do with the shape, right? There's something about the shape here.
It's like kind of bisected. You know,
Like a reverse reflected?
yeah.
Oh,
like maximum.
it's like increase, like when the shape is like this, it's
Uh-huh.
increasing, and when the shape is like.
Okay, so it is the shape. It's this downward shape is getting the green, right? And this upward shape is getting the red, right? The downward shape and the upward shape. But it has nothing to do with the increasing and decreasing of the function, right? It doesn't have to do with where it goes up and down. It's the shape, yeah? Okay, now technically, and this is where not many students see this, technically here's what the definition is and the way we distinguish these two. If you were to take a tangent line anywhere on here, we all agree it's increasing, I mean positive, right? But let's not focus on that. I want to just draw you a couple of these. Ah, man, I keep missing the graph. There are all the tangent lines, a couple of tangent lines on the green, and then here are some tangent lines on the red. Let's see if anyone can tell what the major difference is between those.
The derivative change. The derivative change sign. So
The derivative change signs?
Yeah. For example, in the tangent line of the red, the left side
Mhm.
is positive, then it changes to negative,
And it changed to negative?
and another one it changed from
Negative to positive. Yes, I agree, but what about this one? It doesn't, this derivative, they don't change. So you can't say that for this one. So like, let me show you some tangent lines here. Like I said, not many students see this, okay? So it's all right if you don't. But I want to see if anyone can see the difference between these. See what I'm saying? Like these tangent lines are still positive. Like this never changes to negative.
If prime is bigger than something and the other one is bigger than something.
The derivative, right? The first derivative tells us up and down. I'm telling you, these don't have anything to do with the first derivative. It has to do with the second derivative, but I want you to see from the picture, if anyone can tell me what the difference between these lines are and these lines are for both graphs.
Are they reflected across horizontal?
It's not that. It's not reflections, because I could draw the graph a little different.
Oh, it's just that the ones on the left are sitting on top of the
There it
line,
is.
and the other one
Very
is
good.
sitting on the bottom.
So look, on the greens, all my tangent lines are always above the graph. And on the reds, the tangent lines are below the graph. And same thing here. The greens, right? Tangent lines are above the graph, and the tangent lines here are below the graph. See the difference? Okay? That's what concavity is. Anytime that your tangent line lies above the graph, we say it's concave down. Anytime your tangent line lies below the graph, we say it's concave up. Yes?
Can there be lines like under the graph?
Like this?
Like,
If I draw a continuous function and I draw tangent lines, those tangent lines are either going to be above the graph or below the graph. On a little region, like in this little region, these little lines are below and these lines are above. Okay, well, we can get really caught up in the picture and the geometry of it. Let's just get the actual definition down, and then we'll see. Are there any other questions, though? Okay, let me write the definition down. If f is continuous on an interval I, f prime and f double prime exist. Hold on, I don't have to have the existence. Let me not put a restriction on the derivative, because we could have a cusp, and at the point, derivative doesn't exist. So I'll put, if f is continuous on an interval, so we can draw it without picking up our pencil, then f double prime greater than 0 means all tangent lines are below f. Now, what does that really mean on I? What does that really mean geometrically? It means that the shape has to be something like this, which is called concave up. So if you go and you take a look at the first derivative, you're going to be able to tell me where a function goes up and down. You take a look at the second derivative, and you're going to be able to tell me where the graph is shaped like a bowl, like this, versus, and that's called concave up, versus a bowl the other way, which would be concave down. And I'm not saying it's a parabola. I'm saying it's the shape of a parabola, but I'm not saying it has to act exactly like a parabola does. So if your second derivative is positive, this means all tangent lines are below f, f on the interval. So if f is continuous, then the f double prime being greater than 0 means all tangent lines are below f on the interval. So if I drew tangent lines here, hopefully you would agree they're all below the function, right? All right. And then if I change this, if f is continuous on I, and the second derivative is below, or negative, this means all tangent lines are above f. And so my picture looks like this. And we call this concave down. Most important thing is that to determine the concavity of a function, you're looking at the second derivative as opposed to the first, right? Increase, decrease, you look at first derivative. Concave up, concave down, you look at second derivative. And another easy way to remember this is that second derivative positive looks like this. Second derivative negative looks like this. People who are positive are, happy, they smile. People who are negative are always frowning, right? It's stupid, but sometimes you have to do things like that to remember things. All right. There's one other little definition in here. Suppose F changes concavity at a point C. So I'm going to draw a picture of a change in concavity. This point right here. Do you see where that's where I go from being concave down to concave up? Do you see that that's where that happens? You can almost say it's where the frown, the edge of the frown meets the corner, this corner edge of the smile, right? Where the frown and smile come together? Yeah, do y'all see that? This point where this is happening, I'm calling this C. Then C is called an inflection point. So anywhere you have a change in concavity, you have an inflection point. So it can go anywhere it goes from a frown to a smile or from a smile to a frown. So if I wanted to, I could extend this graph out a little bit to show you that we could have another inflection point like right here, somewhere in there. Because that's where this this smile would turn into a frown. So anywhere where there's a change in concavity, we call that an inflection point. All right? And it's an important point for us. We like that point. It tells us something about the graph. All right? Any questions? So let me kind of reevaluate kind of where we are, even though I've done this already like 10 times today. If we want to know where a function is going up and down, what do we have to look at? Derivative. Where it's positive, where it's negative, right? So logically, if we need to figure out where something is positive and negative, isn't our normal attack on that to first find out where it's 0 and then check to see what happens in other places? That's what we're going to do. And then for concavity, we're going to do the exact same thing, except we're going to be working instead of with the first derivative, the second derivative. We're going to find out where it's 0, and then we're going to check some places around it to see where it's positive and negative. And we put all this information together, we'll be able to get a pretty good idea of what the graph looks like. All right. Now, this leads us to another thing. But this time I'm going to resort back to the first derivative. This is called the first derivative test. Have I used this symbol in here?
Yes.
Yes? Okay, suppose, right? Suppose f prime changes from positive to negative at C at some point. What do you think I can say?
That's the graph is decreasing. That's a low part extra.
it's a local maximum. Think about this. Your derivative changes from a positive to a negative. So somewhere I'm moving along, my derivative is positive, right? So I'm going up, and all of a sudden at some point it's going to change to negative. That means I have to have a local maximum, right? So suppose this changes from at C. Then f of C is a local max. I'll show you a couple of pictures of this. Do you agree all three of these pictures, my derivative goes from positive to negative at C, yes? Here, derivative goes from positive, right, to negative at C. Positive to negative, yes? Okay, what about at C? What's the derivative at C here? 0. What's the derivative here at C? Doesn't exist. Derivative at C here doesn't exist. But C would be critical. These would all be critical numbers, wouldn't they? So if we switch over from a positive to a negative derivative at some point, then as long as this point, C, okay, that C must be in the domain of the function. That's a big thing. C must be in the domain of the function for this to be right. We should have a local max there. So let me give you an example of something where you could get yourself in trouble if you're not paying attention to the fact that that has to be in the domain. So I'll do that in red over here on the side. I'll just draw a picture. How about this function right here? This is actually the graph of the function f of x equals 1 over x squared. If you weren't paying attention, you might determine that to the left of 0, your derivative is what? Positive, and to the right of 0, your derivative is negative. But at 0, your function is undefined. You don't have a local maximum there. And the reason why is because 0 is not in the domain to begin with, of the original function. See it? So be careful. This all works. This is all going to be true as long as that C there belongs to the domain of the original function. Doesn't matter if the derivative exists or not at C. C has to be in the domain. Now, what happens if it changes from negative to plus instead? It's a local minimum. So if you change this negative and positive, then you have a local minimum. And I could draw these pictures again, couldn't I? I just flip them all over. Make this one go like this. Make this one go like this. Make this one go like that. And then I'd tell you again, C has to be in the domain, because then I could do the one that goes like this, and it would go negative to positive. So, is that all right without me drawing it all out again? You okay? That's called the first derivative test. And then that leads us to the second derivative test. Now, the first derivative test doesn't mean that this is the first test that we have for derivatives. It means this is the test that we use that involves the first derivative. Understand the difference? I'm about to give you what's called the second derivative test. It's not the second test in our list of tests. It's the test we use that involves the second derivative. So, second derivative test. Do you understand what I'm saying or not? Yeah. Okay. I'm saying this has to do with f double prime, is what I'm getting at. All right. So suppose, again, f is a continuous function. and suppose f double prime exists near C, and f prime of C equals 0. We have two different things that could happen. One, if f double prime of C is positive, something is true. If f double prime of C is negative, something is true. I'm not going to tell you what they are. I want us to determine them from a graph.
Is that F prime
Of C.
Is it a double prime?
Nope.
Okay.
Nope. Okay, you ready? Let's see if we can get our heads around what this is saying. I'm going to draw you a continuous function. And I'm not going to cut it off or make it a closed interval or anything like that. And what I know is that the derivative, the second derivative, I can find it, okay? Like I can take the second derivative, it exists. And the first derivative at some point is 0. So would you agree right here at C, my first derivative here is 0. F prime is 0 there, right? I should do F prime of C is 0. Everyone agree with what I've written here? So I've got a continuous function, and my second derivative I can actually compute, but the first derivative at that point is 0. That was not enough in the past to tell us that we had a local maximum or minimum. Just because the derivative is 0 doesn't mean you're at a max, right? Here's an example of a function where your derivative at, whoa, I missed that. The derivative at this point is 0, but it's not a maximum, right? But if the second derivative is positive at that point, then it must be concave. If it's positive, concave up, right? So that would mean it would be like this, but our graph doesn't do that, does it? In this picture, our graph is actually what? It's concave down, right? So if you have a point on your graph where the derivative is 0 and the second derivative is, which means the second derivative is negative, then you're looking at a what? Yes? But that point is a what? Nope, inflection is where you change from positive to negative. That's over here. It's a maximum. Local maximum, isn't it? That's a local maximum? So if your first derivative is 0 and your second derivative is negative, that point must be a local maximum. So I'm going to put that right here. Then f of C is a local max. Let me try it a different way. Let me erase this because you all look confused. Let's say I've got some curve. I'm going to draw it, okay? I'm going to draw it with my magic pencil that you can't see, all right? You can't see the curve. It's here, though. And here's what I'm going to tell you. That if I were to look at it at C, I'm going to tell you that the derivative there is 0. And I'm also going to tell you that the second derivative is negative. That means it must be like this, right? Then if you come in to fill that piece in, and you have to have a flat tangent line, and you have to draw it concave down, there's only one way to do that, and that's to force it to be a local maximum. Understand? Where this top line says, let's say you have a derivative at some point that's 0, but this time, when you take the second derivative, you get positive number. That means that it must be concave up, right? Which means that that point must represent a local minimum, right? So it would be something like this. So if the second derivative is positive, then f of C is local min. The second derivative test is a very, very quick way to find local maximums and local minimums. But there's a catch to it. You've got to figure out where the first derivative is 0. Then you have to actually calculate the second derivative and figure out where it's positive and negative, or whether or not it's positive and negative at that point. So I think we've got everything that we need for us to do a couple of examples. All right? We've kind of defined everything that we need to. All right. Yeah, we're gonna start out real basic with just a polynomial function. And these will get harder as we go. So let's say we have the function f of x equals 4x cubed plus 3x squared minus 6x plus 1. Here's what I'd like us to do. Part A, find where f is increasing and decreasing. And that gets to be a pain in the ass to write over and over and over. Okay, so I have a shorter way of saying all this. So find where f is going up and where f is going down. That make sense to you? F increasing and f decreasing. That's the first thing I want us to do. Next thing, find local max and mins. Next thing, find where f is concave up and down. And I have a short way of writing that instead. Instead of doing this, f with like a little upward parabola and then f with a little downward parabola. So that's how I distinguish increasing and decreasing, concave up, concave down, right? And then lastly, part D, find inflection points. So what I want you to do real quick, since we are going to need to look at the first derivative and second derivative, take your first derivative, take your second derivative. You know, let's get those computed first, right? Because we're going to need them in this problem. So let's just go ahead and write them down. I'll stick them up here. What's f prime of x? 12x squared plus 6x minus 6. And then what's f double prime? 24x plus 6. See, the first and second derivative of that were easy, right? But we've seen how sometimes when you take derivatives, they get more complicated. All right, part A. Where's it going up? Where's it going down, right? Well, I know that a function goes up wherever the derivative is positive. A function goes down wherever it's negative, right? So I said the best way to figure out where something is positive and where it's negative is to first find out where it's 0. So what I'm going to do, just to do part A first, is I'm actually going to find the critical points. We've done this before, haven't we? Find the critical points. The critical points are where the derivative is 0 and where it's undefined. So what are the critical points of f? So what do? We take the derivative, we set it equal to 0. That means we take 12x squared plus 6x minus 6 equals 0. Take a 6 out. Does that factor? Does it work? What is it? Is that right? 2x squared, 2x minus x minus 1. That should work. So we get 2 points, don't we? Our two solutions are 1/2 and -1. Questions? Now, I also want to look at where the derivative is undefined. Is that going to happen? No, it's a polynomial. I don't need to look at that. Although I do need to think about it, right? Okay, that's not going to happen because the derivative is a polynomial. So this is where we start to go away from what we did before. Closed interval method, if we're trying to find max and mins and things like that, we just plugged into the original function now, right? It's not what I'm doing, though. So all I've determined, I have not said where the derivative is positive or negative, right? I've only said where it's 0. So what I'll do now, and this is the standard technique, is I'm going to draw a number line. I'm going to plot these 2 points. And those 2 points will break up my number line into 3 regions, won't it? And so what I'm interested in is I know that at this point, right, at -1, my derivative is 0. At 1/2, my derivative is 0. The question is, what's happening to the left of 1? What's happening between these? What's happening to the right of this? When I say what's happening, I mean what's happening to my derivative, right? So I need to pick what we call a test point, something over here. Any number I want, let's say -2. I need to pick a number between these, 0. I need to pick a number over here, 1. I need to take those test points and plug them into, what are we interested in knowing about? The derivative, right? We want to know where the derivative is positive, where it's negative. So these test points need to go into the derivative. And that's where you can run into some trouble, because the biggest mistake I see on this is the closed interval method, we're always plugging points into the original function. Once we get away from closed interval method, we're using test points, we're plugging these into the derivative. So let's test these. What is f prime of -2? What is f prime of 0? What is f prime of 1? So what's f prime of -2? So plug -2 into this. -2, here it's 4, right? 4 times 12. It's going to be a positive number, isn't it? Yeah, I don't really even care what it is. I just care that it's positive, right? So what I know here is that anywhere over here, my derivative is positive. And what does that tell me about the original function then over there? The original function is increase. Nope, we're on the first derivative. Concave is going to be the second. Okay? So the first derivative being positive over here means that the original function is increasing over here. With me? Okay, now we plug 0 in. And all I care about is whether or not it's positive or negative. 0 in here? Negative, right? 0, 0, -6, so negative. So that means my derivative is negative here, which means my original function is decreasing here, right? And then I plug 1 in. And do not count on it to switch, okay? Don't be like, oh, once I find the first one, it's always going to switch. You have to check each one. Okay, f prime of 1, positive. And so my derivative is positive here, means my original function is going up here, isn't it? So for part A, it asks where the function was increasing and decreasing. Can you tell from there? Okay, here's my answer. F is increasing, colon, where? To the left of -1, right? To the left of -1 and to the right of 1/2. And how do we write that? Interval notation. Negative infinity to -1, union, 1/2, to infinity. Now in college algebra, you talked about increasing and decreasing. You could put brackets on the -1 here. And you could put brackets on the 1/2, but it's not necessary to do it. Even though your function is defined here, and those points do exist, and the reason is because in order to talk about increasing and decreasing, you have to have at least 2 points so you can compare which one's higher than the next one. And so leaving out that one endpoint does not ruin anything. So I always just use open intervals then. What about decreasing? At -1 to 1/2, and that's it. Now, I will also point out, all right, that when I was doing this problem, I very subtly made sure that these 2 points were in the domain of the original function. Were they? Yes, they were, right? Because it was a nice polynomial. What was, well, have we answered part A? Where it's increasing and decreasing? Okay. Part B said what? Local max and local min. Okay, so if you go back and you look at the first derivative test said anywhere where our derivative, right, goes from positive to negative, I will have a local max, right? So I'm going positive, and then I'm going negative, and then I'm going back positive. I should have a local max here and a local min here, shouldn't I? Okay. So part B. I'm going to leave that picture up. For part B, we have a local max at what point? X is what? -1? Okay, but I'd actually like to know how high that point goes. So how would I figure out how high that point goes? Plug it into the original function. In other words, f of -1. So we plug -1 in. We get what? -4 plus 3 is -1. Is it 6? I think you get 6 when you plug -1 into the original function. You get 6. Y'all check. Now, where are we going to have a local min?
1/2.
Local min at x is 1/2, and what is the actual minimum value? Local minimum. So plug 1/2 in. While you're doing that, I'm going to fire up my computer because I want to graph this, and I want to check to see that we got it right. I mean, I'm not doubtful that we got it wrong. I just. Anybody get 1/2 yet? You'll have to be able to do that on a test. So it's going to be a little bit tedious in terms of time. Do y'all mind hitting the projector over there, top left corner? Anybody yet? -3/4? Yeah? -3/4. Okay. We good? We've answered part B? What's part C?
Mine were f is concave.
Concave up and concave down, right? That involves the second derivative, doesn't it? So what I'm going to do for part C is exactly the same thing that I just did for part A, except instead of looking at the first derivative, I'm going to be looking at the second derivative. So I'm going to go for C. I'm going to look at the second derivative. I'm going to find out where it's 0. I'm going to look at the second derivative and look at where it's undefined. So it's almost like I'm doing critical points again, but I'm doing it with the second derivative. So where